Hola, chicos.
Hola, profe.
¿Sí me escuchan bien?
Sí,
Excelente. Vamos a esperar un poquito, unos 5 minutos, a ver si se conectan los demás y empezamos.
sí, profe. Oiga, profe,
Sí.
¿no sabe si vamos a poder hacer asesorías presenciales?
Mm, pues habría que pedirlas. El problema es que como yo también doy clases en el Madrid,
Ok,
no me, o sea, digamos, dependiendo de dónde pongan el salón, pues podría o no.
ok,
Sí, pero dejen abrir.
ok, sí. Es que se me complicó un poco la tarea, la verdad.
Mm.
O sea,
Ok, igual hoy con lo que vamos a ver también vamos a pues, afianzar el tema, ¿no?
ok,
Pero sí. Pero sí, sí, pues se podría. Igual el examen de la semana que viene, pues tiene que ser presencial, ¿no?
ok, ya. O sea, ¿ya va a haber examen bien o es como de prueba?
No, o sea, el examen es la próxima semana,
Ah, ok,
¿no?
ok.
Entonces, hoy
O sea,
vamos a
¿es el
acabar de
examen
ver.
parcial, profe?
¿Perdón?
¿El examen parcial de la próxima semana?
Sí, ¿no?
Ah, ok.
Sí, es el lunes, que luego abro el sílabus, pero según yo es el lunes. No, perdón. Ah, no, perdón, es el jueves 26.
Ah, ok.
Ok.
El jueves.
Híjole. Okay, guys, so we're going to begin the class. Today we're going to do a couple of problems about chemical reaction to reinforce the things that we saw last week. And I know that many of you have questions about the second problem. I'm not going to solve those questions today because I just uploaded the solution for those two problems. So please look for it into, well, I send you a notification or an email through Blackboard, so you can see it through a mix view. That it's a PowerPoint plugin that let you record sessions and so on. So if you have questions about those, we can see them on Thursday, for example. Okay, but first look into the solutions, so to see if you have any questions about those. Okay, so today we're going to solve. The first problem is about chemical reaction, and the second one is about combustion. And if we have time, I'm not sure that we're going to solve a third one about combustion too. Okay. We were talking about with other students that the second partial exam is on Thursday of next week. I'm going to ask for a classroom so we can have it on, so we can have a presential exam, of course, right? What else? Well, that's more or less it. If you want to see the presentation on your own computer, I uploaded a file into the presentation of chemical reaction. I updated today, so if you want to download it so you can see the other problems that we're going to solve, you can, right? What else? Yes. On Thursday, I'm going to give you an activity for the equilibrium of phases, of gas phase and liquid phase, most of it, right? That is going to give us information on how to solve problems with equilibriums of different phases. Okay. Okay. So, any questions before we begin the presentation? Okay, so what we're going to do is this problem over here. This problem over here that it's about the methanol production. It's the same reaction as in the second problem of the homework, but in this case we are injecting an inert gas. So if we have an inert gas, you need to treat it differently, and we need a purge. If we don't have a purge, we can't solve this problem. We could solve this problem, but it's not ideal because the inert gas is going to start accumulating into the reactor, and well, that would give us a lot of problems, a lot of headaches if we have a real plant, right? Okay, so I'm going to start reading it, and I'm going to give different some advices about this one. Okay, just making sure that it works. Okay, so it says methanol is produced in the reaction of carbon dioxide and hydrogen, right? So it says carbon, hydrogen. The reaction it's already balanced, right? So we have all the atoms in both sides, and it says here. It says the fresh feed to the process contains hydrogen, carbon dioxide, and 0.4% of mole of inerts, right? I'm going to represent as an I. The reactor effluent passes to a condenser that removes essentially all the methanol and water formed on none of the reactants or inerts, right? The other substances are recycled to the reactor. To avoid buildup of the inerts in the system, a purge stream is withdrawn from the recycle. The feed to the reactor, not to the fresh feed of the process, contains 28% of mole, 70% of CO2, 28 mole percent of CO2, 70 mole percent of hydrogen, and 2% mole of inerts. The single pass conversion of hydrogen is 60%, right? This is important. of 60%. Calculate the molar flow rate of molar composition of the fresh feed, the total feed of the reactor, the recycled stream, and the purge stream for a methanol production rate of 155 kilomoles per hour, right? Okay, so the first thing we need to do, of course, is to do the diagram, right? So before we begin, any questions about any of the things that this problem is asking or telling us? You could raise your hand or either mute your microphone and ask the question.
What does it means that the single pass conversion of hydrogen?
Okay, in a process where you have more than that you have more process than just the reactor, you have an overall conversion that is for the whole process using all the process units and so on. And this one that it says the single pass is from the inlet of the reactor to the outlet of the reactor. So just in that one, right? Just for the reaction inside of just the reactor, not the whole process.
Okay, thank you.
Yeah. You're welcome. Any other question, guys? Okay, so if you don't have any other questions, please draw the diagram that you think you need for this particular process, right? We have seen recycles and we have seen purges in mass balance problems. So it's more or less the same thing. So take 5 minutes to draw the diagram and we will see the actual diagram in a few seconds. If you have any questions while you're doing it, please let me know.
Teacher, it says that to avoid build-up of the inerts in the system, a purge steam is withdrawn from the recycle. What does that mean?
Remember that when we did a couple of problems where you have the recycle stream is going for example, in this case, from the condenser to the inlet of the reactor, right? But if you only do the recycle and you don't add a purge, you're going to start building up the inerts, right? You're going to start having more inerts and more inerts and more inerts inside of the reactor. And that, of course, is going to raise the pressure and so on, right? So that's not ideal. So to avoid that part, you have to add a stream that goes out of your recycle to purge the inert gas, right, in this case. Yep.
Okay, thank you.
Mm-hmm. Okay, so do you have a diagram?
I think I have.
Okay. Okay, so the diagram, well, I'm going to talk about it here. It says that you are going to have a reactor, right? So you're going to have a reactor, right? Has a fresh inlet, right? And then that reactor is going to go to a condenser, it says, right? That removes essentially all the methanol and water. Okay, so I'm going to go here. This is the reactor, and this is the condenser, right? And it's telling us that we have an outlet that has essentially all the methanol and all the water, right? So we have CH3OH, and we have water over here, right? And it says this current is going to be recycled to the, well, for the reaction to take place, right? And it says that to avoid the buildup of gases, we're going to need a purge. Okay, so a purge could be a stream getting out of here, right? And here, of course, if we have in the condenser, here you're going to have CO2 and hydrogen in the inlet. Then in the outlet, you're going to have CO2 that didn't react, hydrogen that didn't react, methanol that was produced. Sorry, here we are missing the inerts. Water, and of course, the inert gases, right? So if in the condenser we separate all the water and all the methanol, of course, in these three currents, in the currents that get out of the condenser, we're going to have, in all those three, we're going to have CO2, hydrogen, and inert gases, right? So that's the whole point of this purge, right? To eliminate these inert gases. Well, so they don't build up in the reactor, so the pressure doesn't get too high, and so on, right? Okay, so that should be more or less what you have, right? But remember that just drawing the picture is not enough, right? We have to put all the different components and the unknown values that we have. So we have these values, well, this diagram, right? When I put all the information in it, right? So we have an N0, right? So here, we don't know the exact composition of it, right? But we know the amount of inert gases that it has, right? At the fraction of them. Then we have the inlet to the reactor. Here, I put it 100 moles right now because it's easier if we do it with the reactor than if we do it with the stream that goes out of the condenser that was asked to be 155 kilomoles, moles, right? So instead of doing that, we have a lot of information about the reactor, right? But we don't have too much information about the condenser or the overall process. In the reactor, we know the reaction, we know the composition that gets into that reactor, and we know how the inert gases behave, and we know the percentage of conversion, right? So we have a lot of information for the reactor. So I'm going to add the 100 moles over here, and if we have 100 moles, it means that we have 2 moles of inert gases. Because those gases are inert, in the outlet of the reactor, we should have exactly those 2 moles of inert gases, right? So then those gases go to the condenser, and in the condenser we reduce the temperature. By reducing the temperature, we condensate the methanol and the water, right? Because those condense, we can separate them in the bottom of the condenser as a liquid, right? And then we're going to have a gas phase in the upper part of the condenser that is going to have all the CO2, all the hydrogen, and all the inert gases, right? And because we don't want the buildup, we're going to separate this stream. This part over here is just a separator, right? Remember that in a separator, the only thing that changes is the number of moles, not the concentrations. So if you if you pay attention to the, yeah, let me put another curve. If you pay attention to the fractions that I assign, let's say this one, for example, for CO2, we have the fraction is called X5C, right? 5, it's the current, and C is the carbon, and X5H is the hydrogen. And of course, the inert gases, we can obtain it through subtraction, right? 1 minus X of the carbon and X of the hydrogen. That gives us the fraction of inert gases, right? So if you follow the fractions, you're going to see that all the fractions are the same in the streams that get in and out of the separator, because, well, that's what a separator does, right? The only thing that changes is the amount of mass, right? So the only equation we have for the separator, of course, is that N5, it's equal to NP plus NR, right? That's the only equation that we have. And then in the mixer, we're going to have, well, the same 3 components, right? CO2, hydrogen, well, carbon monoxide, hydrogen, and inert gases. So we have all the information. So now what we need to do is, of course, to obtain the degrees of freedom of the global process, the reactor, the condenser, the mixer, and the separator, to see how can we solve this particular problem. Okay, so I'm going to change software to do that particular part, because I don't like drawing in PowerPoint. So let me share the other one. Okay, so here we have the information, right? The same information that we did a couple of seconds ago. So what we need to find is the degrees of freedom, right? So I'm going to begin drawing the degrees of freedom for the global process. Remember that the global process, it's a box that encapsulates all the streams. Okay, so we have that, right? So we have that boundary box, the yellow box, and then we can find the degrees of freedom. Because we have a reactor inside of the boundary, we need to treat these degrees of freedom as a reactor. We can't do it just by mass, because, well, we have a reactor inside of it, right? So remember that we have 3 methods: the atomic, the molecular, and the extent of the reaction. For this particular problem, because we have information about the conversion of hydrogen, 60%, right? It's easier to do the molecular method or the extent of the reaction method, either one, right? So if you remember how to obtain those degrees of freedom, they behave the same way. So I'm going to put here the global process. The global, and we're going to do it by molecular / extent of the reaction. We use the same values for the molecular and extent of the reaction, so the degrees of freedoms are the same. Okay, so to obtain the degrees of freedom, we need to know the number of unknown values. The number of unknown values. In this case, to the global process, we have N0 x 0C, right? That is the amount of CO, right? So we have 2, and then over here we have N3 and N4 that we have for the methanol and water. And then in the purge we have NP, X5C, and X5H, right? So we have 3, 4, 5, 6, 7. 7 unknowns, right? Then to this one we have to add the number of reactions, right? The reactions. In this case, we only have 1 reaction. Then we need to subtract the number of different compounds, number of molecules of molecular species. The molecular species will have carbon dioxide, hydrogen, we have carbon monoxide, hydrogen, methane, well, methanol, water, and the inerts. So we have 5, right? And then we don't have any extra equations, right? Or other equations. We don't have other equations because the one that we have, that is the 60% conversion of hydrogen, as we talk about, is the one step or for the reactor. So it's not for the global process. It's just for the reactor. So in this case, we have zero other equations, right? So here we have 8, and then we have 3 degrees of freedom. So of course we can't begin in this particular process, right, in the global. So then we're going to do the degrees of freedom for the reactor, right? So again, it's the same things, it's the same procedure over here. So the unknowns in this case, we have complete knowledge of the inlet, and in the outlet we have N1, N2, N3, and N4. So we have number of known species, we have 4. Then we have 1 reaction again, 1. Then we have the same 5 different species: carbon dioxide, hydrogen, the inert gases, the methanol, and water, right? So we have 5 different values. So this is plus, this is minus, and this gives us 0 degrees of freedom, right? Okay. And for all the other process, for the mixer, for the separator, and for the condenser, we use regular mass balance degrees of freedom. So unknown values minus the number of equations that we have, right? So we're going to do the condenser. And the condenser, we're going to have 1, N1, N2, N3, and 4. Then we have the methanol and water, so we have 6. Then we have N5, 7, X5C, 8, and X5H, 9, right? So we have 9 unknown values, right? And we have 5 different components. 5 different components, so this is the equations that we can have. We don't have any other equation. So we have 4 degrees of freedom over here, right? Then we do the mixer. In the mixer, we have unknown values. We have N0, X0C, NR, X5C, X5H, right? So we have 3 over here, 3, 4, 5 different 5 unknown values. And in the mixer, we have the same number of equations of the components. In this case, we have 3 different components because we have only carbon dioxide, hydrogen, and inert gases. So we have 2 degrees of freedom. And the last one is the separator. In the separator, we have 3 unknown values, that is N5, NP, and NR, right? And we only have 1 equation, right? So 2 degrees of freedom again. Yep. So the only way we can begin to solve this problem is through the reactor. Okay? So through the reactor, if we solve the reactor, right, what we're going to solve, let's put it here. If reactor is solved, then we're going to find values for N1, N2, N3, and N4, of course. That is going to cancel some of the degrees of freedom of other units. For example, the condenser, right? We have 4 degrees of freedom in the condenser, but if we solve the reactor, we're going to have, well, minus those 4 that we just found, and then the condenser will have 0, right? If we solve the reactor, that's the only thing that is going to change, right? But we can then solve the real condenser afterwards. And if we solve the condenser, we're going to solve N3 and N4 and N5 over here, and the excess, of course. So all these values, right? and that will give us the concentration in the recycle stream and in the purge stream, and that could lead us to, for example, to solve the global, right? The global or the separator or the mixer. We can go through all those, right? So in this case, I'm going to propose. I'm going to propose steps to solve, right? So the steps would be to solve the reactor. Then to solve the condenser, right? If we solve the condenser, then we can solve the recycle, the mixer, for example, because we have information about it. And if we solve the, then we can solve either the global balance or the separator, right? Either way. Yeah. Okay. So these are the steps that we have to follow, right? We have seen that we can solve this problem using either the molecular or the extent of the reaction, either one. We have 0 degrees of freedom. And with that, we can obtain the reactor, then the condenser, and then so on, right? So for this particular exercise, we're going to team up in teams of, let me see how many participants we have. We have 23, so let's say it's in teams of 4 and one of 3. I'm going to do a random mix of you guys, so you can work in separated groups. Okay, so I'm going to give you 2 minutes to write down if you need any information of this plot. Remember that you have the presentation on Blackboard, so if you need to have it. In these small groups that are called breakout rooms, you can ask for help too, right? You can raise your hand and that kind of things. Okay, so you let me know if you have any questions or anything, so we can solve it, right? Remember to follow these steps: the reactor, the condenser, the mixer, and the separator, and you will find the answer, of course. You have any questions before we begin the breakout rooms, guys? Anybody, guys?
The presentation is in where it says presentaciones or
Blackboard. In Blackboard, have presentaciones, and then it says chemical reaction.
Oh, okay.
It's already updated, so it's a new file.
Okay, thank you.
Okay. Okay, so let me put out the breakout rooms. Okay, so remember, in the breakout rooms, they work as Zoom, right? You have the video, you can chat, you can use your microphone, you can use the whiteboard, and so on, right? So you can share your screen, and that kind of things. Okay, so let me open those. Guys, you have to join your breakout room. The Zoom has told you that you should join, so please do. We have Paula Carrion, Marco Natera, and Sebastián Rodriguez without joining to their breakout rooms.
Difícil esto, ¿eh? Vamos a ver esta cochina. Vamos.
Hola chicos, me vine a colar.
Hola, profe.
Profe.
Oigan, con eso de escribir, si tienen un iPad a la mano, pueden aquí en la parte donde dice Share Screen, le pueden poner que que puede utilizar el iPad como, pues, como una tableta para escribir.
Ah, ¿en serio?
Sí, se supone. Bueno, al menos de este lado se puede.
Ok.
¿Cómo van?
Ahí vamos.
Pues, ahí vamos, profe. Está un poco difícil, ¿no? Bueno, como agarrarle la onda, creo.
Sí, pues un poco, ¿no? Es parte de la práctica.
Profe, ¿cree que nos pueda, bueno, no sé si sea la tarea como que nos sirva como para practicar y todo eso para el examen?
Mm,
O si hay algunos ejercicios extra.
pues yo creo, o sea, con eso yo creo que tienen suficientes, la verdad.
Ok.
O sea,
Pues,
finalmente la mayor parte de los problemas de reacción química se parecen mucho, por ejemplo, a este que están haciendo ahorita, ¿no? O sea, hay un solo reactor y hay diferentes procesos unitarios que hacen la separación, ¿no? Entonces, se parece bastante a esto.
ok.
Digamos, lo que cambia es finalmente el número de reacciones o la información que tienes al respecto, ¿no? Pero se abordan de la misma manera. Tienes que buscar los grados de libertad y con los grados de libertad, pues bueno, plantear una estrategia y con esta estrategia pues, resolverlo, ¿no?
Ok.
Voy a dar una vuelta a otro chat y ahorita regreso.
Sí, profe.
Profe, gracias.
Los otros dos elementos, o bueno, los productos, por así decirlo. Ajá. Entonces, para el N1, según yo, lo que tenemos que hacer es ver con cuánto reacciona, por así decirlo. Y luego eso restárselo, o sea, sería como 100 por el punto 28 menos tu, como simbolito este, es que no me acuerdo cómo se llama, pero bueno, el de la reacción.
La E, ¿no?
Ajá, como la E1, por así decirlo.
Ok.
Hola chicos, me vine a colar a su chat, ¿cómo les va?
Pero, pues, bien, creo.
Ok. Sí, de lo que estás hablando es la letra griega esa rara, se llama el avance de la reacción, ¿no?
Ah, eso. Perdón, es que no me acordaba.
Bueno, si tienen alguna duda me pueden mandar un mensajito y voy a ir a otros chats. Ahorita regreso.
Ok, bro.
Entonces,
Pero no sabemos cuál es el reactivo limitante. O sea, no sabríamos si...
sí, es el hidrógeno porque nos sobra 14 de CO2.
Hola chicos, ¿tienen alguna duda por el momento?
Pues ahí vamos, profe.
Juan Iván.
Todavía no, profe, gracias.
Vale.
Sí, gracias.
Bueno, regreso al rato.
Gracias.
Hola, profe.
¿Cómo les va chicos? ¿Alguna duda?
Pues es que empezamos a hacerlo por el de extent, pero, o sea, no sé, tenemos como una idea de poner como los moles de CO2 y ya ponerle como moles iniciales de CO2 menos la E de extent y así,
Ajá.
ir como cancelando.
Sí, lo que puedes hacer es que como sabes que va a reaccionar el 60% del CO2
Ujú.
en un paso y tú ya sabes cuánto entra, ¿no? Porque ya tienes la composición que es a punto 28, ¿no? De CO2. Entonces sabes
Ok.
que entran 28 moles al reactor, ¿no?
Ajá.
Son los moles iniciales y los moles finales los puedes obtener justo a partir del 60% de conversión, ¿no? Si se reacciona al 60%, pues entonces tiene que quedar 40%, ¿no? Digo, perdón, era con el hidrógeno. Disculpa.
Ah, ok. El hidrógeno. Entonces, o sea, 60% que entra.
60% reacciona
Ajá.
y 60% pues no reacciona, ¿no?
40, ¿no?
Digo, 40%, perdón.
Ajá. Y entonces si lo hacemos con el hidrógeno serían, ¿qué? O sea, 70 moles iniciales.
Con el sí, 70 moles iniciales, justo.
Y, o sea, hago como una regla del 3 ahí, o como, ¿qué hago? O sea,
¿No?
no.
O sea, haces una operación, ¿no? Tú pones que el número de moles finales de hidrógeno, que en este caso es N2, es
Ajá.
igual a lo que no reacciona, que entonces es 0.4, ¿no? El 40% por el número de moles iniciales, ¿no? Que son 70. Y eso te da el número final de moles de hidrógeno después de la reacción.
Ok.
Y si escribes tu fórmula ¿cómo se llama? Del avance de reacción, pues vas a tener que el número de moles finales es igual al número de moles iniciales a menos 3 veces el avance de la reacción, ¿no?
Ah, ok. Ajá. Sí.
Y entonces ya de ahí sacas el avance de la reacción y lo aplicas para todos los demás componentes.
Ah, ok. ¿Y cómo saco cuánto vale la E de
Por eso,
extent?
primero, o sea, con que sabes que el 40%, como sabes que el
Ajá.
40% no reaccionó, sabes cuánto hidrógeno va a salir al final, ¿no? Cuánto va a ser N2, ¿cierto?
O sea, porque, o sea, NH2 final sería, o sea, los 0.4 por 70, que serían 28, ¿no?
Exacto.
Pero el inicial es lo que no entiendo.
Pues el
O sea,
inicial son los 70, ¿no?
sí, sí. Y ya el inicial son los 70 y ya de ahí saco mi E y ya de ahí la puedo sustituir en las otras ecuaciones, ¿no?
Exactamente, porque el avance
Ah,
de la reacción es el avance de la reacción, no tiene que ver con el componente en particular, ¿no?
ok.
Nada más
Sí.
recuerda que para el hidrógeno, como tiene 3 de coeficiente estequiométrico,
Ajá.
la ecuación del avance de la reacción es el número de moles finales es igual al número de moles iniciales menos
Entre
3
tres.
veces
Ajá.
el avance de la reacción.
Ah, sí. Sí.
Vale,
Va.
voy a
Vale.
dar una vuelta
Gracias.
a otros.
Sí. Gracias.
In the separator, the inert gases, will they go totally or they recycle?
Está, profe, su micrófono está silenciado.
Okay, sorry. Okay, so in the separator, if you see the fractions, that go into the separator and out of the separator are the same, right? So yes, in the separator, you're going to have inert gas, well, carbon dioxide, hydrogen, and inert gases that go into the recycle stream and into the purge, right?
Okay.
So yeah, you have inert gases in all the currents. Yeah.
Okay, thank you.
You're welcome. See you in a bit. Hello, guys. Are you here? I don't see nobody. Jesús, Marco, Sebastián. You have your microphone's muted, so if you want to talk, you need to unmute it. Okay, I'll be back then.
Sí, profe.
Sorry, somebody was talking and I log out.
Sí, ya estamos trabajando, profe.
Ok. Vale, pues, ¿dudas?
No, creo que no, pero bueno, si tengo duda ahorita le mando un mensaje.
Ok, perfecto.
Gracias, profe.
Nos vemos al ratín.
Espérate.
Pero como por...
Pues espérate, Alonso, estamos usando un 0 más. Porque si están entrando 100, no pueden salir 280. Serían 28, 28, 14, 20.
Hello.
Okay. Harper,
Uh-huh.
we have a question. As in the we already got the all the N1, N2, N3, and N4.
Okay.
But if I'm right, I think in the condenser, doesn't the N1 should be the same as the X5C?
Well, the amount, yes, but the fraction, no. Okay, so after the reactor, you don't have fraction, right? You have a total amount of moles.
Yeah.
Right? Yeah, but it is the same. Yes, of course, the number of moles in the current that gets out of the condenser should be N1, right? For CO2, N2 for hydrogen, and 2 moles of inert gases, right?
So we can say that the N5 we're just going to add the N1, the N2, and the inert gases.
Exactly.
And then from that we're gonna get the X, which is the model. No, the fraction, right?
Exactly.
Oh, okay. Yep. Thanks.
I will join you in a second. Hello.
Hey.
You had a question over here, Emiliano?
Yes. We want to know, okay, the N5 is the sum of the inert gases, the CO2 and the H2.
Exactly.
Right?
Yep.
So we don't have a relation of NR and NP?
Not yet, no. But you can obtain it, well, even if you don't have a relation, you can obtain it through the mixer or through the global process.
Okay.
Ah, sí.
Okay, thank you.
You're welcome. See you in a bit.
Que según yo, si es así, es lo que no estoy muy seguro. Profe.
Hello, guys. Yes.
Por cada 3 moles de hidrógeno sí se produce un mol de cada producto, ¿verdad?
Sí.
Ok, gracias. Entonces, ya que tienes eso, simplemente por la multiplicación, te sale que tienes 28 moles de dióxido, 28 moles de hidrógeno, y 14 de metanol, 2 de inertes y 14 de agua. ¿Entendiste, Jess?
Sí, pero necesito verlo. Es que no, o sea, si me lo explicas así, no entiendo nada. Necesito verlo. No puedes compartir tu pantalla o algo. Mándame una fotito.
Es que literal lo estoy haciendo en papel. Pero ahorita veo. Y profe, ya que tienes la salida del reactor, pues esos ya son las cantidades que salen en cada corriente, ¿no? ¿O hay que hacer algo más?
No, digamos, bueno, para el condensador no, o sea, para el condensador asumes que como se están separando completamente el metanol y el agua, pues puedes decir que N3 y N4 son iguales, ¿no? Y para la corriente 5, pues obviamente el número de moles en la corriente 5 será igual a la suma de los monóxido de carbono, de hidrógeno y de inertes, ¿no?
Ajá, pero la corriente de reciclaje no contiene nada de inerte y en la que se sale el inerte no tiene nada de los otros.
No, en la de reciclaje, no, a ver, ese sí es un separador. O sea, digamos, en el punto donde tienes la purga, ahí lo único que estás haciendo es separar la corriente. Entonces, en las tres corrientes, en la de entrada al separador y las dos de salida, en las tres tienes dióxido de carbono, hidrógeno e inertes. Pero con la misma composición. En unos 5 minutos les resuelvo esa parte. ¿Qué pasa?
No podemos hacer una clase presencial. ¿Me pueden, por favor?
Ya sé que odias esto, Jessica, pero pues no es
No
tan fácil.
entiendo. Es que no puedo así, soy muy visual y si no, o sea, necesito estar ahí con usted y interaccionar personalmente porque si no, no puedo entender.
Pues deja ver qué tan factible es, porque el problema es que como yo también doy clases en el Madrid todos los días, pues los
Pues
salones...
vamos al Madrid, profe.
El problema es que los dejen entrar.
Ah.
Esa es la bronca, por eso tengo que ver.
¿Y en
el Starbucks?
En el SEM,
¿En el qué?
en Campus SEM.
No, a Campus SEM me queda lejísimos. Yo como doy clases acá, o sea, voy a SEM y ya no doy clases en el Madrid. Ese es el problema.
¿Y los sábados?
Pues, los sábados no me encanta la idea, pero bueno, deja ver qué podemos aprender. ¿Vale?
Ayuda, por favor.
Bueno, los lunes sí podría ser más fácil.
¿Los lunes?
Ajá.
¿En dónde? ¿Por el Madrid o por dónde?
Pues sí, pues o sea, es que yo vivo a 3 cuadras del Madrid y del TEC.
¿De Ciudad de México?
Ajá.
Opino que por el Starbucks, profe.
Pues sí, puede ser.
Por donde usted quiera, profe. O sea, literal.
El problema es que el
Estoy ahorita
Starbucks...
en Campus Santa Fe.
El problema es que el Starbucks, el piso de arriba, está deshabilitado.
¿En serio?
Sí, la otra vez pasé y no sé qué le habrá pasado, pero está cerrado.
No, yo no me acerco ahí, capaz si se me cae encima. Ya sufrí suficiente.
Esa parte no sabía.
Bueno, pues dejen, veo, y además...
En el Costco.
En el Costco. En las mesitas.
Hay mesitas, ajá.
Bueno, vamos a ver qué arreglamos, ¿va?
Sí, por favor, profesor.
Vale. Unos 5 minutos más y lo vamos resolviendo acá con todos, ¿va?
Vale.
No te arriesgues.
En la reacción y el 40 sobran.
No.
Hello.
Al revés.
Oye, aquí está.
Hola, profe.
Profe, tenemos una duda.
A ver.
Si lo vamos a hacer como en molecular, tendríamos, por ejemplo, hacemos el balance de CO2, ¿no?
Sí.
Entonces ponemos 100 moles, que son los que pusimos que entran, es igual a N1, que es el CO2, más el 60% de hidrógeno, ¿no?
O sea, la duda es que es lo del single pass conversion.
Eso es que, y dice sobre el hidrógeno, ¿no?
Ajá.
En un paso es que de la entrada al reactor a la salida al reactor reacciona el 60% y por lo tanto no reacciona el 40%.
Ok.
Entonces, ya cuando si sabes que reaccionó el 60% de hidrógeno, pues entraban 70, ¿no? De hidrógeno.
Ajá.
Entonces, 60% de eso reaccionaron. ¿Sí? Entonces, si lo hacen por molecular, pues entonces tienen que hacer relaciones, ¿sí? Entonces, por ejemplo, el número de moles de carbono, de monóxido, perdón, de dióxido de carbono que reaccionaron, pues tiene que ver con el número de moles de hidrógeno que reaccionaron, que son 70 por 0.6, ¿sí? Y luego por la relación estequiométrica que existe entre ellos. Es decir...
Que es 3-1, ¿no?
Ajá, bueno, 3-1, pero
Okay.
cuando lo escribas en la relación lo pondrás como entre 3, ¿no?
Ajá.
Para cancelar el número de moles.
Pero entonces sería hacer 100 moles, o sea, como está en la pantallita, profe, así 100 es igual a N2 más... ¿O cómo?
Pero no serían los 28 que tenemos del CO2.
Porque mira, tú lo que tienes es, les voy a escribir una, ¿no? Entonces, acá tienes el número de moles.
¿Cómo puedo escribir?
Porque soy mago, Manu. Lo único malo es que no funciona del todo bien. Entonces, el número de moles en la corriente de entrada, en la corriente de salida, ¿no? Tendrán que ser igual, pero pues escribe y no escribe, no te creas. Tendrán que ser igual al número de moles, lo voy a poner en letrero y luego lo escribo, ¿no?
Sí.
Estos son de hidrógeno, multiplicados por la relación que existe, ¿no? Entonces, por cada 3 moles, escribe pero chapísimo. Por cada 3 moles, ¿qué onda? ¿Por qué esto no está funcionando? Ya no puedo anotar. Algo pasó.
Se acabó la magia.
Se acabó la tinta, mano.
A ver, si quiere, díctame, yo lo pongo.
Acá está. Entonces, 1-3, ¿no? Ese sería el número de moles de CO2 que reaccionaron, ¿no?
Ajá.
Por tener el número de moles finales, pues haces la resta, ¿no?
¿Qué dice aquí, profe?
Ya entendí. O sea, el N2 ya lo conocemos con la información que nos dan, ¿no?
Es la relación Pato.
Ya entendí.
¿Sí?
Ya.
Entonces, el número de moles de hidrógeno que reaccionaron, pues son los 70, ¿no? Por el 0.6.
O sea, 42.
Ajá. Y es la relación, ¿no? ¿Cierto?
Sí.
Entonces, el número de moles de CO2 que reaccionaron. Entonces, se los restas, ¿no? A los 28 creo que eran.
Sí.
A los 28 iniciales le restas pues lo que reaccionó, que es ese 70 por 0.6.
Entre 3.
Entre 3.
Ok. Y así hacemos lo mismo con el agua y con metanol, ¿no?
Ajá, haces las mismas relaciones.
Ok.
Pero esta vez solo es la producción, ¿no? Porque no tienes nada, metanol no tienes al inicio, ¿no? Entonces todo el metanol formado, todo el metanol a la salida es el metanol que se produjo, ¿no? Que se formó.
Ajá.
Con el agua.
Pero, ¿cómo se llama? O sea, el metanol, por ejemplo, está 1-1 con el CO2. Entonces,
Ajá.
lo mismo que entra de CO2 es lo que sale de
Ahí te
metanol.
conviene hacerlo con el hidrógeno porque es el que tienes, ¿no? Entonces, por ejemplo, N3 es el del metanol, ¿no?
Sí.
Entonces, N3 es el del metanol, será igual al número de moles de hidrógeno que reaccionaron.
Ajá.
La relación estequiométrica, ¿no? Que es 3-1, ¿no?
Ok.
El número de moles que reaccionaron, pues es los 70 por 0.6. ¿No?
Profe, y si fuera con el extent de la reacción, habría que hacer el sistema, ¿no?
Pues sí, lo que haces es que primero calculas el número de moles finales de hidrógeno, que lo calculas a partir de la relación del 60%.
Ajá.
¿No? Y entonces con eso vas a saber que el número de moles finales de hidrógeno, este es el extent, ¿no? El extent del número de moles de hidrógeno finales será igual al número de moles iniciales, ¿cierto?
Ajá.
3 veces esa cosa que no me sale nunca, ¿no?
Ok.
El avance de la reacción, ¿cierto? Okay. Entonces, si tú ya sabes cuál es el número de moles iniciales y el número de moles finales, tú ya puedes calcular estos dos.
Ok.
Entonces, puedes obtener el avance de la reacción y escribes todos y escribes todos igual, o sea, o escribes el avance de la reacción para cada uno y ya los obtienes, ¿no?
Este final sería el 70 por el punto 6.
No, por punto 4, porque es lo que no reacciona, ¿no?
Ah, claro.
Entonces 70 por 4. Baja 70 por punto 4, o sea, 28, ¿no? ¿Cierto?
Sí, sí, sí.
Sí.
Eso. Y entonces ya de ahí puedes sacar el avance de la reacción.
Ok.
¿Vale?
Ok, gracias, profe.
Bueno, voy a pasar al chat grupal pues, ya para resolverlo, ¿no?
Ok.
Está bien.
Vale. Okay, so welcome back, guys. I hope the breakout rooms were good in the interactions and so on. Okay, so we're going to solve the problem. Many of you were in the right path, so I'm just going to do it. So if you have any other questions to share, right? So let me go into the program. Okay. So we have over here our problem, and we said that we were going to solve the reactor first, right? And I told you that the molecular was the easiest process, so that's the one that I'm going to use. So in this case, what we have to do first is that we know the conversion of hydrogen, right? So we have to begin with hydrogen. So to obtain the number of moles of hydrogen in the outlet, that is N2, we're going to have that 60% was the hydrogen that was converted. So 40% is the hydrogen that wasn't converted, right? So we're going to have that 0.4, that is the 40%. Of the 70 moles that we have 0.7 of a molar fraction and 100 moles. So we have 70 moles of hydrogen. Then this is going to be the amount of moles that didn't react, right? So that gives us 28 moles of hydrogen at the outlet, right? So we know that 0.6 times 70 is the amount of moles of hydrogen that was converted, right? That is the 42, right? 42 moles of hydrogen were converted, right? So in for the molecular balance, we're going to use this value, right? The hydrogen that was converted to obtain all others. So for example, so for CO2, the balance of CO2, we know that the CO2 we have that the output is equal to the input minus the amount that reacted, right? Or was consumed. Okay, so the number of moles of CO2 at the end, that is N1, is going to be equal to the input, that in this case is 28 moles, right? Minus whatever reacted, right? So for that one, we're going to use the 42 moles of hydrogen that reacted. So we know that 42 moles of hydrogen reacted, right? And then we see the stoichiometric relation, right? We have for each mole of CO2, we need 3 moles of hydrogen. So to convert these moles of hydrogen to moles of CO2, we need to do that factor, right? So each 3 moles of hydrogen needs 1 mole of carbon dioxide, right? So if we do this operation, we're going to find that the CO2 balance is 14 moles at the end of CO2, right? That is N1. And we do something similar for the methanol and for the water, right? So the number of moles of methanol, that is N3, is going to be equal, in this case, just the output is going to be equal to the generation, right? So the output M3 is the output, and the generation we use again the number of moles of hydrogen and then the factor, right? The stoichiometric factor, that is 3 moles of hydrogen for each mole of methanol. Yep. So we substitute the values. In this case, it's 42 moles that reacted, and then 1/3, and the number of moles is 14 again. Of CH3OH. And the last one is the number of moles of water. That it's the same thing, right? It's the 42, right? Moles of hydrogen that reacted divided by 3 moles of hydrogen for each mole of water. So again, 40 moles of water, right? So I think everybody reached that this particular point in the problem. So now we solved the reactor, so we have N1, N2, N3, and N4. So now we know the outlet of the condenser, right? In the condenser, now we're going to do the condenser. In the condenser, we have, what we have is that, well, N3 and N4 is the same values, right? So N3 in the condenser is going to be the same 40 moles of methanol, and N4 is going to be the same 14 moles of water, right? And then we have N5, right? N5 is the number of moles, the number of moles of carbon dioxide, hydrogen, and inert gases, right? So N5 it's going to be equal to N1 plus N2 plus 2, right? So N5 it's equal to 14 plus, sorry, no, sorry. So sorry, N1 is 14, yes, plus N2 that is 28 plus 2. So this gives us 44, right? In that particular current. And to obtain the fractions, well, we know we're going to have two different equations, right? For the fractions, we know the total amount of moles, what we need to do the balance of CO2 and to do the balance of hydrogen to obtain those. So the balance of CO2, because its mass is the input, the output, it's equal to the input, and the same thing in the hydrogen, right? Output is equal to the input, right? So the output in this case is the X5H times 44, that we know that value already, right? That is N5. And this is going to be equal to the number of moles of N2, right? And N2 is 28 moles of hydrogen, right? So that's the balance of hydrogen. Sorry, I mixed that up. I mixed them up. Sorry, I'm going to change that. Terribly sorry, guys. So this was for the hydrogen, and this one is for the CO2. And for the CO2, we have that X5C is the CO2 times 44. Should be equal to the number of moles of carbon monoxide, that is N1, that is 40, right? So with these two equations, what we're going to find is that the fractions are X5H. It's equal to, let me see, 0.634, and X5C, it's going to be equal to 0.3182. And that makes that X of 5 of the inert should be 0.04545, right? Okay, so this gives us the fractions in that particular current. So we have all this current completed, right? And that means that we have X5, X5G, and X5H in each case, right? So with that, we solve the condenser completely, and then we need to solve the other part of the problem. So let me erase this one. Okay. So now I told you that we could solve the mixer, right? So in the mixer, in the mixer, what we're going to have is that the total balance, the total mass balance, or in this case molar balance, it's going to be the input, it's equal to the output, right? The same, so N0, that is the fresh feed over here. So N0 plus NR, that is the ones that are going to be mixed, should be 100 moles, right? And then we have the balance for the inert gases. So in this case, we have the the part that goes into the fresh feed is going to be 0.004 times N0, right? Plus the one that gets into the with the recycle, that it's 0.004 45. Sorry, I'm using a second zero. 0.04545, right? Okay, so these times NR that we don't know yet, right? And this should be equal to 2, right? But it's 0.02 times 100, right? And with that one, we can obtain, if we solve these two equations, we are going to obtain that N0 should be 61.4 moles, and NR should be equal to 38.6 moles. Okay, so that gives us the total mass. Okay, but we have here a fraction that we don't know, right? We have a fraction here that we don't know, that is the fraction of carbon dioxide in the fresh stream. We'll have to do a CO2 balance to solve that. And again, its input is equal to output, and we solve this one, right? So we're going to have that N0 times X0C. So N0 0C should be equal to plus the one that goes into the recycled stream should be equal to, well, in this case, 28 moles, right? Because we know that already. Okay, so we have most of these values. N0 is 61.4 times X0C plus NR, that is 38.6 times X5C, that is, sorry, give me a second, X5C, that is equal to 0.318. And this is equal to 28, right? So X0C should be equal then to 0.740. And I run out of time in this for this class. Okay, it's 9:55. But the things that you need to do is just to solve either the separator, right? Missing steps. One, solve the fraction, the molar fraction of H2 in the inlet in N0. Then solve either the global or the separator to find NP. And that's it. With that, you finish the problem, and that's most of it, right? The only things that you have to check is the different questions that the problem asks, but with the information that you have here, you can solve those. So that's it for today. We will see each other on Zoom again on Thursday, because we need to address a couple of problems about combustion. I'm going to give you an activity for Monday. Do you have any questions about anything, guys? Nope, everything is fine. Okay, so then see you on Thursday, guys, please. I will send you an email either way. Okay.
Profe, yo solo tengo una duda. O sea, todo lo que entra, porque todo lo que entra en el reactor no es lo mismo que todo lo que sale. O sea, no, o sea, los 100 moles que entran, ¿por qué no son los 100 moles que salen?
Ah, porque en reacción química los moles no se conservan.
Ah, ok.
La masa sí se conserva, pero los moles no.
Ok, va.
Entonces, como tienes un factor de 3, un factor estequiométrico, un coeficiente estequiométrico de 3 en el hidrógeno, no se puede mantener la cantidad de moles.
Profe, no alcancé a ver la última respuesta. O lo veo en el video ya de repetición de clases. Ahí ya lo último, lo de mixing steps, ya no lo pude al terminar de copiar.
¿Esto?
Yo no veo nada. Ah. Ya. Pero déjame mejor le tomo screen y ya.
Vale, bueno, igual, si no voy a subir el video, obviamente.
Sí. Aquí está. Ya. Muchas gracias, profe.
Okay. Bueno, de nada. Ok, entonces, bueno, we will see each other on Thursday again on Zoom to solve a boiler problem. Watch the video that I uploaded to the platform Mix. So if you have any questions for it on either Wednesday or Thursday in the class or in the advice sessions, okay? See you on Thursday, guys.
Yes, teacher. Have a nice day.
You too.